Hi everyone, this is the first in a series of 2 videos covering the integration topics for the International Baccalaureate course Maths Standard. In this video we're going to go through anti-differentiation, indefinite integrals, methods of integration, integration by substitution, and then resolving the constant. So recall, if f of x is equal to 4x to the power of 5, then f dashed of x would be 20x to the power of 4, because the 5 comes down, multiplies by the 4, and then we've got x, and we drop this power by 1. So that gives us 20x to the power of 4. Now, anti-differentiation is the reverse. So we want to go from this point, the derivative, back to the function. So if we were to work backwards, then if our derivative were 20x to the power of 4, then the function would be 4x to the power of 5. So let's see if we can figure out what the rule is. So remember, we said before that the 5 comes down and then the power drops by 1. We can see it's sort of the reverse here. This power is going up by 1. So here's the rule. If the derivative is equal to x to the n, then the function is x to the power of n plus 1 divided by n plus 1. So in simplest terms, it means raise this index by 1 and then divide by that new number. Now, it also has a plus c on the end, which is constant. I'm going to talk about that later. So this process is called anti-differentiation, or finding the antiderivative. Let's look at some examples. Find the antiderivative of f dashed of x equals 3x squared. So this 3 is going to hang around, just like with differentiation. And then I'm going to raise this power by 1 and divide by the new power. So I'm going to get 3x cubed divide 3. And then I'll cancel these 3's out. So our answer will be x cubed plus this constant. What about this one? Again, just like with differentiation, we're going to go term by term. 2 hangs around, x to the 4 divide 4. Minus 3x squared divide 2. What about this one? This is 5x to the 0, so it becomes 5x to the 1 divide 1. But you're actually used to this. Okay, when you differentiate this, you just get the constant. So if we've got a constant and we're finding the antiderivative, the x sort of pops back in. Right, tidy that up, and our answer will be x to the 4th on 2 minus 3x squared on 2 plus 5x plus c. Now let's look at why there is a constant. So suppose we're asked to differentiate y equals 2x cubed minus 4x plus 7. So we're back to differentiation. The 3 comes down, multiplies by the 2, x, drop this power by 1, minus 4. Suppose we were given this as the derivative and asked to find the antiderivative. What would we get? So now we're doing our other method, our reverse method. So this is going to become 6x cubed divide 3, take 4x. And tidying that up, we get this. Is there any difference between this and this? So because the 7 has disappeared from the derivative, there's actually no way to get it back. Do you know why it's disappeared? So remember, this is x to the 0. And when I bring that 0 down, it wipes the whole thing out. So because it's been wiped out here, I can't tell what it was. Initially it could have been 11, could have been minus 12, who knows. So by putting the plus c on the end, we're acknowledging that there could have been a constant. There might not have been, it might have been 0. But we put plus c to say there possibly was a constant, but we don't know what it was. Now the process of finding the antiderivative is called integration, and this is the notation we use. We're going to go through why we use that notation in the next video, but for the moment it looks like a funny curly S, and here's the function that we want to find the antiderivative of, or the integral of, and this dx means with respect to x. So this is how we would read this. Find the integral of 7x squared minus 5x plus 4 with respect to x. Okay, so here's some examples. Now, looking at that first one, the integral of cos x dx, we're not going to use that power rule that we just learnt, x to the n plus 1 divide n plus 1. We're going to use our logic from what we know about differentiation. When I differentiate sine, I get cos. So when I integrate cos, I must get sine. So it's going to be sine x plus c. E's easy, isn't it? The derivative of e to the x is e to the x, so the integral of e to the x must be e to the x. And then finally, this one down here is an interesting one, isn't it? Before we answer that, let's turn it around. We've got x to the negative 1. Let's use our power rule. This goes up by 1 to x to the power of 0, and we divide by 0. What's wrong with that? Can't have 0 on the denominator. So this doesn't work by the power rule. This is actually ln, or log base e. We did learn that when we were doing the derivative. So it's equal to log base e. We should put the x in absolute values like this, but I tend not to in this video. But at higher level, you would need to, but standard, probably get away with it. That means x has to be positive, okay, because log's only defined for positive numbers. So log base e of x plus c. So here's a copy of all the formulas that you get in the formula booklet. So we've got our power rule. We've got 1 on x. The integral of 1 on x is equal to log base e of x. We've got two trig integrals. So integral of sine x is equal to negative cos x, and the integral of cos x is equal to sine x. And of course, the integral of e to the x is equal to e to the x. Now, let's have a look at this little cartoon here. It says differentiation. Start. Try applying the chain rule, the power rule, the quotient rule, the product rule. Are you done? Yes. No, go back in and do it. Differentiation is really nice. There's always a way of doing it. Okay, you can keep using quotient rules, product rules, and chain rules, and eventually it'll may get very complicated, but you get there. Integration's not so easy. Okay, so you can try applying integration by parts we're not going to learn. Substitution we are. Are you done? No. Well, try partial fractions and all of this sort of stuff. Phone a mathematician. Oh, this is really true, this cartoon. Okay, there's a lot of functions that we just can't integrate. Some functions like e to the x squared don't have antiderivatives as we know them. I have to qualify that and say there is an antiderivative, but we're certainly not going to learn it in this course. But it doesn't look like an e to the x thing. It doesn't look like a function. So there are some things that we can't do. We don't have a product rule, we don't have a quotient rule, and we have a limited chain rule with integration. So unlike differentiation, there are no product or quotient rules. So if we want something like this, we have no choice. We have to expand the brackets. Let's have a go at this one. So we're going to do FOIL on it. And we don't need to tidy that up, do we? Nope. 4x squared minus x cubed minus 4 plus x. Okay, we're going to integrate term by term. 4x cubed divide 3 minus x to the 4 divide 4 minus, what's this one? 4x. Remember the x will pop back in, plus x squared on 2 plus c. There it is. Then we look to see whether we can tidy it up, but we can't. Here's another one. There's no quotient rule, is there? But it's an improper fraction or an unbalanced. It's top heavy. So that means that we can split it up like this. And we're just going to split it into two fractions. So I've got 2x squared on x minus 1 on x. So that's going to be the integral of 2x minus 1 on x dx. Okay, let's integrate term by term. 2x squared divide 2 minus, what's this one? Log base e. So I'm going to get x squared. I've actually tidied that up in one go. I hope that's all right. This was 2x squared divide 2. The 2's cancel out. Minus log base e of x plus c. Now there is a limited chain rule. It's actually a reverse chain rule. So it's kind of undoing what we've done when we differentiated. It's often used with the power rule, but not always. So let's have a look at how we differentiate 4x minus 5 all cubed. So the 3 comes down. We leave this alone to the power of 2 times by the derivative of the second function. So it is 3 comes down, multiplied by 4x minus 5 all squared times by the derivative of this, which is 4, and that gives us 12, and then in brackets 4x minus 5 all squared. So let's have a look how we might go the other way. So we've got 12 outside of 4x minus 5 all squared dx. Now logic tells us that if the derivative of this is equal to that, then the integral of this must be equal to this. So we're trying to get back to this. So we're going to try and apply our chain rule. 12 hangs around. We're going to get 4x minus 5 cubed divided by 3, and then what do you think we'll do? So you can see the 12, there's the 3, there's the 3. We're going to divide by the derivative of this. Okay, we don't want to divide by the integral of this. That would make it really disgusting. So that's what I mean by it being a reverse chain rule. We're trying to get rid of the thing that we did here. 12 divided by 12, of course, cancels out, so we do end up back where we started. Let's have a look how we go. So we're going to leave this alone, raise the power by 1, divide by the new power, divide by the derivative of this. Goes 5, divide 5, times by, on the bottom, derivative of this, which is 3. So it'll give us a 15, and then plus c. Sine 2x. Okay, you can see I've got a function in a function. Let's start with the outer function first. The integral of sine is negative cos. So I'm going to get negative cos 2x. Then I'm going to divide by the derivative of the second function, which is 2. Did you see that? Here we've got e. E stays the same, doesn't it? And then I'm going to divide by the derivative of the second function, which is 4. Okay, may need to do some practice on those. So why is the chain rule limited? Well, the chain rule will only work as long as you don't introduce a new variable like x when you divide by the derivative of the second function. Let's have a look what that actually means. Look back to our little friend here, which I said wasn't able to be integrated. E to the x squared. So suppose we just did it by what we consider to be the chain rule. So we've got e stays the same, and then we're going to divide by the derivative of the second function, which in this case is 2x. So can you see how I've introduced an x that wasn't there? Okay, one way to tell whether this is the correct function is to differentiate it. So let's do that and see whether we get back to e to the x squared or not. So it is a quotient rule. U is equal to e to the x squared and v is equal to 2x. Let's do the derivatives. U dash will be e stays the same times by the derivative of the second function, which is 2x. And v dash is just going to be 2. All right, now we need to construct our quotient rule. So d dx of e to the x squared divided by 2x is going to be v times by u dashed minus u times by v dashed all over v squared. Okay, tidying this up, we get e to the x squared and then in brackets x squared minus 1 all over 2x squared, and that's actually as simple as it gets. Now remember, if we integrate this and get this, then if we differentiate this, we should get back to e to the x squared, and we don't. Okay, we get this monstrosity. We've made it more complicated because we introduced this second variable. Okay, so it's a no-no. So the chain rule will only work providing we don't get new x's, basically. So which questions can we use the chain rule with? Let's have a look at these. So here, our outer function is sine our inner function is x cubed, so when we differentiate that we get 3x squared. So we can't use the chain rule with this one. Okay, this one here, this is a log. Our second function is 3x minus 5. The derivative of that is 3, so that one's fine. We can use the chain rule with that. And this last one, we've got a couple of functions here to look at, or a couple of terms. Here's the one that may well be the issue. Our second function is 4x, and the derivative of that is 4. And so there's no problem with that. And obviously no problem with minus 5x or 6, so that one is okay as well. Here's another way they might ask a question. By differentiating x ln x minus x, or otherwise find the integral of ln x. Okay, so if we're not sure really what that means, let's start off by doing what they suggest. Let's differentiate x ln x minus x. Now we do have a product rule here, but I'm actually going to do it straight into my working out like this. Let's have a look. You can set it out u equals x, v equals ln x, do the derivatives and then construct it. But it's just here. So it is u, which is x, multiplied by the derivative of ln x, which is 1 on x, plus v, which is ln x, multiplied by the derivative of u, which is just 1. And then don't forget this last term here. We're doing term by term now. Minus derivative of x is 1. Okay, if that's too fast for you, stop and set it out, the way that you want to. X divided by x is 1, so they actually cancel out. And what we end up with here is 1 plus ln x take away 1, which of course is ln x. Alright, the derivative of this is equal to that, so the integral of this is equal to this. Does that make sense? So sometimes they might ask you to differentiate something and then find the integral of another thing, and you'll be expecting it that it will be almost the same, if not exactly the same as this. Okay, so there's our answer, plus C. Here's another example. Differentiate 2x squared minus 1 all to the power of 4 and use the result to find the integral of x, and then in brackets 2x squared minus 1 all cubed dx. Okay, let's do what they say. Let's differentiate this. It's a chain rule. 4 comes down, 2x squared minus 1 cubed, multiplied by the derivative of the second function. Now you might be going, oh, we've introduced an x. But remember that that's perfectly fine for differentiation because anything goes. It's integration where we can't introduce an x. Let's tidy this up. 4 4s 16x, and then our bracket thing. Okay, if we differentiate this and we get that, then when we integrate this, we get this. How close is this to that? Pretty close, except for a 16. And a 16 is not going to cause us any problems because it's a constant. So let's just finagle this so that it looks like 16x. So we're going to have a 16. We're going to divide by the 16 here so that we sort of undo it. Times by 16, divide by 16. And now we've got the perfect thing here. When we integrate this, we get that, and we're just going to end up with a 16 on the bottom. Okay, let's return to our little friend e to the x squared. Now remember how we can't integrate that, because when we integrate e to the x squared, we have to divide by 2x, which is the derivative of this second function. Now in this case, the 2x is kind of sitting there for us. So we could do something sneaky here and just say that happens to be equal to e to the x squared plus c. Have a look at it. When I differentiate this, I get e to the x squared times by the derivative of the second function, which is 2x, which is that. Now, there is a method for doing this, a more formal method called integration through substitution, which we're going to do next. But some of you will be able to see that. And this is a perfectly valid method to go straight to the answer. So let's look at how we might do that using substitution. The question will look like this. By making the substitution u equals x squared, find the integral of 2x e to the x squared. So we're going to substitute for this second function here. We start off like this. Let u equal x squared, and we differentiate that. Of course, we're going to get du dx, not dy dx, because we're differentiating u with respect to x. Now, Leibniz's notation, so he's one of the founders of calculus, gave us some notation so that we could split it up like it's a fraction. So this dx can come over the other side, which is kind of helpful here. So 2x dx, can you see the 2x there and the dx there? That's going to become du. And e to the x squared is going to become e to the u. Now when you substitute, do it all in one go. You shouldn't have an x left at the end. Let's have a look at how we might do this wrongly. So 2x dx is du multiplied by e to the u. It's true we've only got u's now and not x's, but there's something wrong with it. Do you know what it is? This du should go at the end. This means integrate e to the u with respect to u. So it should look like that. Now this is pretty easy, isn't it? Okay, it's just integrating e to the u, so that is e to the u. Don't forget the plus c. And our final step is to substitute back. So instead of u, we're going to write x squared. And that's an important point. So finish off your question by substituting back for x. Here's another one. By using the substitution u equals 2x squared minus 1, find the integral of x, and then in brackets 2x squared minus 1 all cubed. So we can see this is going to become u cubed here. But what's x and dx going to become? Let's start with let u equal 2x squared minus 1. Differentiate. So du dx is equal to 4x. Split it up and take the dx over here. Now we're trying to play a matching game. Okay, we've got an x and a dx. Here's the x and the dx. We don't want the 4. Bring it over here. All right, we're ready to substitute in. Instead of x dx, I'm going to put du on 4. And instead of this, I'm going to write u cubed. Okay, see how I've put the du at the end? Now this is pretty simple. This quarter here could come out the front if you wanted to get rid of it. That's going to become u to the power of 4 divide 4. And tidying that up, I get u to the power of 4 on 16, but we've substituted back. So instead of u, I've put 2x squared minus 1. And that's actually our answer. Here's another one. By using the substitution u equals 3x squared minus 5, find the integral of x divided by 3x squared minus 5. Okay, we're starting with let u equal 3x squared minus 5. Differentiate. Du dx is equal to 6x. Take your dx over the other side. All right, what have we got? This is going to be u. We want x dx. Okay, we don't want that 6, so let's take it over here. All right, now we're ready to substitute. So instead of x dx, I'm going to write du on 6. And instead of this, I'm going to write u. Now have a look what I've done here. I've been sneaky. I've decided to throw the 6th out the front to get it out of here. So I've got du on u. This is okay to write it like this. You could write 1 on u du, but that's perfectly acceptable. You just can't have the du before the function. This is a log, isn't it? So it's going to be 1/6 ln u plus c. What have we got to do now? Substitute back. There's our answer. We can substitute cos functions, so it doesn't have to be those power rules sort of questions. We could substitute u equals cos x here to find the integral of sin x on cos x dx. It's going to start the same way. Let u equal cos x. Differentiate. Du dx is equal to negative sin x. Take your dx over. Looking back at the question, we want sin x dx, not negative sin x dx. So I'm just going to throw this negative over here. Substituting in, that's going to be u. Sin x dx is going to be negative du. It's another log. I've put the negative out the front. It's going to be ln u plus c. And now we substitute back in. Do you recognise this? This is tan x. So this is actually a method for finding the integral of tan x. It's negative ln of cos x plus c. Okay, we're going to look at one more. This one's a little bit beyond the course, but it's an interesting application, so I thought we'll do it anyway. So you can see how this one's a little bit different because the derivative of this is not sitting out here. So we're still being told to make a substitution, so we'll start with this. Let u equal x plus 1, and then do the derivative. So du dx equals 1, take the dx over, and we get du equals dx. Now let's have a look what happens. Here I'm going to have the square root of u, and here I've got du. But I haven't managed to get rid of this x. Normally the x is down here. That's okay though, because we've got this expression here. We can easily turn that around and make x the subject. So x is equal to u minus 1. So when we substitute it in, it looks a little bit different. We've got in brackets u minus 1 and then the square root of u du. Right, we're going to expand this out. So I've got u times the square root of u minus the square root of u du. And now I need to turn that into index form. So it's u to the 3 halves minus u to the half du. Now, this is quite ugly, this question from now on, but that's okay. It's more to show that there are other questions that we can use this method for. So we're going to raise this power by 1 and divide by the new power. And we're going to do that with both terms. Now I'm going to flip this fraction up. So remember, this is dividing by 5 halves. So I'm going to times by 2/5. And here I'm going to times by 2/3. I've taken the liberty of also putting the x plus 1 back in and substituting back in. Now you could make that a nicer looking fraction, but we're not going to bother because it's not really the point of what I'm trying to show you. So this is another type where you would use a substitution. Now if we're given extra information, we're actually able to figure out what the value of the constant is. And this is called resolving a constant. So here's an example. Find the integral of f dashed of x equals 4x cubed minus 3 root x, given f of 4 equals 1. So this is the extra piece of information here. We're going to start the same way. F of x will be the integral of f dashed of x. You can see how I've changed root x into x to the half. Okay, let's integrate. 4x to the 4 divide 4 minus 3x to the 3 halves over 3 halves. Okay, we can cancel these two, and I'm going to turn this around to be 2/3. Okay, so there is our expression that we would normally get. Okay, but we want to figure out what c is. So we're told that when x is 4, f of x equals 1. So let's substitute that in. F of 4 will equal 4 to the power of 4 minus 2 times 4 to the 3 halves plus c, and that's all going to equal 1. So here's an equation that we can solve. 4 to the 4 is 256. 4 to the half is 2. 2 cubed is 8. So I end up with 256 minus 16 plus c equals 1. And making c the subject, c is equal to negative 239. And so our answer is f of x is equal to x to the power of 4 minus 2x to the 3 halves minus 239. So I just want to present a curious case involving logs. So find the integral given f of 1 equals 0, where f of x is equal to the integral of 1 on 2x dx. Now I'm going to do this two ways. I'm going to do it as a chain rule to begin with, and then we're going to take the half out and do it the other way. So doing it as a chain rule, this is going to be log base e, and of course we're going to divide by the derivative of the second function. If I do it the other way by taking the half out, I don't have to do a chain rule. It's going to be equal to a half, or ln x on 2. Now look at these two different answers. So depending on the method, it appears like we get a different answer. Let's see if we can work that through and get this. Remember that log of a product means we can separate that out. So that's log 2 plus log x. And I could split that into 2. but I still don't have the same answer. Do you see? I've got this bit extra. So let's substitute in those values. Remember when x was equal to 1, f of 1 was 0. So 0 equals ln 2 over 2 plus ln 1 over 2 plus c. That's 0. And so in this case, our constant is going to be equal to negative ln 2 over 2. How about over here? Substitute in f of 1 is equal to 0. Now in this case, this is 0, so the constant is equal to 0. So the difference in both of these cases is that the constant has a different value. So both answers are actually valid, and you would get both of them correct, but the constant is different. Now let's see if we can work that through and get the same answer. So here we are here. We had ln 2 on 2 plus ln x on 2 plus c, and there's our c. Have a look what happens. Ln 2 on 2, take away ln 2 on 2, of course is 0, and voila, we do end up with the same answer. Here's a past exam question. Find the integral of x e to the x squared minus 1 dx. Okay, it's one of those substitution questions. You can do it through substitution or you can do the shortcut. It's up to you. It's worth 4 marks, so providing you show some working out, you should get all 4 even if you use the shortcut. Let's do it through substitution though. Let's let u equal x squared minus 1. Differentiate, du dx is equal to 2x. Take the dx over the other side. Now we want to match x dx, so this 2 will come over here, but I actually haven't done that. Let's substitute in and see if you can figure out what I've done. So you can see the du on 2, and then I've got e to the u. If you want to do this last line here and do du on 2 equals x dx, go for your life, that's fine. Okay, the half, I'm going to throw out the front. The integral of e to the u is e to the u, and then it's going to be plus c. Substitute back. Our answer is e to the x squared minus 1 all over 2 plus c. Part B, find f of x given that f dashed of x equals x e to the x squared minus 1 and f of negative 1 equals 3. So same question that we just did, but now we're going to resolve the constant. So we found out that f of x was equal to e to the x squared minus 1 all over 2 plus c. So when x is negative 1, f of x is equal to 3. So 3 is equal to, see how I've put the 1 in there, e to the 1 minus 1 over 2 plus c, that's e to the naught there. E to the naught is 1. So c is going to equal 3, take away a half, which is 5 on 2. And then don't forget to rewrite it at the end. So f of x is equal to e to the x squared minus 1 plus 5 all over 2. Here's another one. Let f dashed of x equal 3x squared all over x cubed plus 1 all to the power of 5. Given that f of naught equals 1, find f of x. So same thing, it's a substitution. Doesn't tell us to use substitution, however, and we can see the exact derivative of this is sitting up there. Let's do it through substitution though. Let's let u equal x cubed plus 1. Differentiate, du dx is equal to 3x squared. See how I've been sneaky there and split it apart already? And that's going to match the entire numerator. So let's set up the integral. There it is there. 3x squared dx is going to be du, and down here I'm going to have u to the power of 5. Now, we can't integrate this, we need to bring it up the top. So it's u to the negative 5 du. Let's integrate. So we're going to increase the power by 1, so negative 4, divide by the new power, plus c. Now just tidying that up and substituting back for x cubed plus 1, we get this. So I've brought the negative out here because we don't put it on the denominator. And I've brought this u to the negative 4, I've taken it down the bottom. So that's x cubed plus 1 to the power of 4 plus c. Now we need to do our substitution. So we know that when x is 0, f of 0 is 1. So that's going to be 1 equals, and then I'm going to substitute the 0 in here. So I get 1 is equal to negative a quarter, because that's 1 to the power of 4 there. And so C is going to equal 1 1/4 or 5 over 4. And go the extra step and substitute that in. So we get f of x is equal to negative 1 on 4x cubed plus 1 to the power of 4 plus 5 on 4.